everyone, my name's Alex. I'm an engineer and my passion is design, development and prototype production of all sorts of engineering solutions. In this episode we want to do some modifications on the Steadyrest of the Emco V13 lathe. These modifications are supposed to take care of some annoying features on this Steadyrest which have bugged me over the years many times, and these modifications are long overdue. And now that I have a critical job coming up, which unfortunately I cannot show on YouTube, but this critical job gives the immediate impulse that I have to do this right now. And in case you're interested what I do to the Steadyrest, join me, why not? So the Emco Steadyrest. There's two annoyances we want to get rid of in this episode. The one is this one here. You see? You can't turn it out of the bed, you have to loosen it a large way and then you can turn it out of the bed. And this is an added annoyance whenever you use it. So let's get rid of this here. And the other one is I want to modify these bearings here. Now these bearings are one of the two options of the classical textbook Steadyrest. These are the sliding bronze bearings. Now these bronze bearings, the textbooks always say they are so good because they are so rigid in comparison to the ball bearings. Be that as it may, but I believe this only to be true when you pre-machine these bronze shoes to fit the diameter of your workpiece. Because otherwise it's kind of a line contact here, and I'm not sure if that is much more rigid than a ball bearing. But be that as it may, I didn't do the math on it, it's just a gut feeling. The big annoyance with this is whenever you have soft material like plastic or aluminum, you can see it here, then what happens here is that this chews itself up. So these bronze shoes versus the workpiece, they chew themselves up, and this is really neither a good solution nor is this a proper solution, and that's why I want a second set of arms here, or support arms, whatever you call them, with ball bearings in them. So in order to make a second set of support arms, a second set that carries ball bearings in here, I ordered up some hard chrome plated hydraulic rod. Why did I particularly choose hard chrome plated hydraulic rod? Well, it's not that expensive. It's available in the 28mm diameter like the originals are. The outer diameter is already tight tolerance, centerless ground and hard chrome plated, so this should be a solid basis for the sliding fit in here. And the core of the material is quite soft, so we should have an easy job machining the features that carry the ball bearing here. So let's see how that goes. Who wants to mess up the shiny new chrome plated surface? Well, I don't. That's why I clamp it in the collet here. And first we have to face for length, and I'm using a positive cutting geometry insert here. And in order not to wear all the time on the susceptible tip of the tool, I'm taking a rather deep cut here so that the hard chrome player only wears on a further back part of the cutting insert, so as to get the most life out of that insert. Here one of the two big chamfers on the front side. I take one rough cut and one finish cut. The intention behind this is to load the susceptible positive cutting edge tip only a limited amount of times by going through the hard chrome layer. That's good. Then there's the second chamfer. That's the back side. Part is already turned for length. And the back side needs a large chamfer. This is the end that is inserted into the Steadyrest, and this end will also get the left hand thread later on in the video. This is preparing just a center hole for the tailstock when we do the milling. Yeah, off to the milling machine. Now to the left of the frame here is my Walter UTA dividing head, which is a very handy way of clamping this, because we have to machine the part from at least two sides to define or to create the features for holding the ball bearing. And the tailstock on the right end is necessary because I take fairly deep cuts with the end mills, and I want the part to be as rigidly clamped as possible. You may be able to get away with a cantilevering clamping setup here if you take shallow depth of cuts, but you'll see, you'll understand later on in the video. I believe, at least. So let's use this 20mm diameter solid carbide end mill for making the flats on the outside of these quills. And I'm just using minimal lubrication here, some mist lubrication. Of course we have to go machine through the hard chrome layer, which can be hard on the tool life, and that's why I'm rather taking quite deep cuts here, so as to limit the time they have to spend in the hard chrome layer. So let's check the dimension of that flat here. This dimension is uncritical. I just do this with the micrometer to keep an eye on the wear of the end mill, but the wear was really not notable. Parameters were good, I think. And here we start with the 6mm, believe it or not, high-speed steel end mill to clear out the slots for the ball bearing. And for the same reason that I mentioned before, I'm taking one deep cut here. This is kind of foolish to do this all in one deep cut, and I only dare to do this here because I can make very sure to clear out all the chips with the mist and compressed air lubrication that I have here. If you couldn't make sure that the chips are cleared out immediately after the cutting process, then you run a very high risk going such a deep cut here. And this high-speed steel end mill is already mid-life, I would say, and I wanted to limit the amount of time it has to dwell in the hard chrome layer, so that's why I'm doing this in one roughing cycle and one finishing cycle, and it worked out nicely. Same here. This is the slot for the set screw that clamps the quills and registers the quills rotation wise. So the width of that slot is, it's not critical, but it should be fairly close to dimension. And I also go one roughing cut and one finishing cut. And believe it or not, that high-speed steel end mill held up for all the three quills, no problem. This is of course the hole for the ball bearing. Here Mr. Idiot could run the danger of drilling through the tailstock tip. Fortunately I recognized that danger, so that's why I retracted the tailstock tip a little bit. Of course then you have to keep an eye on your feeding pressure, that you do not push down the part. So of course reaming with oil. so that we have a good fit with that dowel pin that holds the bearing. Countersinking. So, nice. Next is the bearing, of course. These burrs, they look really nasty, but they're only very thin, as you can see from the filing process here. They're readily and easily removed, so they're very thin. The file I'm using here is an old one, because the hard chrome layer is also not easy on the files, and these files are kind of expensive, these precision files, these Swiss-made files that I like to use. So I always keep in stock the old ones, because the heart aches when you throw away such a Swiss-made file, even if it's dull. It's always good for qualitatively checking hardness or doing something like this, so that's why I keep them around. Now this is a very slight and fine round over and finish with the bristle disc. There are abrasive particles in that bristles, and in order to give the surface a more homogeneous appearance, I use the abrasive stick here to clean everything up a bit more and round over the edges a bit more. We're talking microscopic chamfering here, because the abrasive action of that stick, of that rubber stick, is really very fine. But it's good because on the touch with the hands, it feels good. It's a defined corner, but it's not sharp like a knife anymore, which is what we want here. So far so good. That's the milling work done. Surfaces don't look too bad. I think we can work with that. So let's put in the thread and the central hole. So it's back to the lathe. I'm always making sure to clean up the surface very well so that we do not clamp on chips, of course. Chips are dirt.
Don't forget to wipe your dirt.
You boys got something to say to me? Why don't you talk into the microphone?
So here we have the problem that we have to drill through that cross hole, and that may misdirect the drill. So what I rather do is I inside turn that first part of the diameter that sees the cross hole, and I turn it to, I don't know, maybe 20 microns or so smaller than the final drill diameter. And we have some kind of guiding feature through that first interrupted part here for that drill, and we only have to drill to depth, and that works nicely. So you see that that material that was left in the center is now completely gone. That's part of the design, which is very nice for fabrication too. And next is to invert the part, drill the smaller hole. That first hole was drilled before, that clears the quill adjusters. And this hole is now the core hole for the M14x2 left-hand thread. So M14x2 millimeter left-hand thread. So we need a pitch of 2 millimeters. That's shifter code FC. Let's see, C, and gotta turn the spindle. F, C, that's good. And the left hand For the left hand we need to reverse the feed direction. But first let's plunge a thread relief into the back side. And I do this with 3 individual plunges, shoulder on shoulder, and a cleanup cut here. Actually, this is a universal inside cutting insert holder that I made a few years ago, and it carries these custom ground inserts that you can make from shanks of end mills or thread tabs. And here I exchange it to the threading insert. It's very easy grind on the D-bit grinder. And this flat spot on the side that's ground in one setup helps to align the insert, so you only have to push it in or let it extend as far out as you want and then clamp it. So it's very easy to use and convenient. For checking the threads I need to take out one of those spindles, because who has an M14x2 left hand go or no go gauge? Or even a bolt? That's classic! That's just a tight tolerance pin, and that's the spindle. So left hand threading, we start on the inside and let the carriage or the bed slide move to the right out of the part. And the depth of cut I'm taking here is maybe in the beginning 0.3 of a millimeter in the diameter, and then later on the increments get smaller down to 0.1 of a millimeter on the diameter, and then in the end the spring passes and maybe adjustments for 50 microns or so on the diameter. Yes, I know, can be tiring to watch. I hope you're not snoring already. So let's check that. It's a bit tight yet. So 2 or 3 more spring passes, maybe 50 microns more on the diameter, or a bit less. Still 1 more spring pass, or 2. No, 3? Yes, 3. Nice. So let's check the fit. What is it? Lefty? Tighty? No. What? I get confused so easily. Yes, that looks nice. Works all the way in. Good. And so finally let's just clean up the lead in. Or is it the lead out? Whatever. Okay, and this times 3. So here's a fun fact for you. The project had a really nice head start because before I started machining everything and after I had finished the design, I ordered up the materials, and the hydraulic rod material I ordered, the 28mm diameter, the supplier mistakenly sent me the wrong diameter, that's 25mm diameter. And I didn't even recognize it after I had already cut and started machining it. And the bearings that go into these arms, they are 6002 RS type bearings. And I ordered them from a different supplier, and they sent me the wrong bearings, which are they sent me 6003 2RSR bearings. So calculate the odds, right? So these are shims to space the outer ring of the bearing away from the carrier arm. So they are 200 microns. I didn't have 200 micron shims in stock, so I use two 100 Mikron shims, and we're going to press fit it all together with these M6 tolerated pins. I had to custom shorten them to fit the length, but that should be no problem. That's a bit tight. I'm gonna use just one on one side. Please don't tell my accountant that I'm using one less shim here. Come on out here. So just one on one side. Now that fits nicely. So there's no danger to waste the bearing because there's no load on the outer ring during this press fit. The load goes through the pin and through the axial shims. So you see I can turn the outer ring during the pressing process, no problem. So there's no danger of wrecking the bearing. But now we have to hammer the pin in so that it is flush with that surface. And I'm going to hit the bolt. Hopefully not the camera. So this surface here is flush so that the set screw in here that is used to tighten the arms has a free passage here. That's good. And this one here is protruding just with the chamfer that's necessary for pressing it all in. And this should all move in nicely into the hole of the Steadyrest. So let's see about that. You know it, and I know it. This is actual working speed, right? Ah, if it just were. So important aspect in the design of these modified arms is that we can make use of the full capacity of that Steadyrest, and that should be a bit more than 100 millimeters. So of course a larger capacity would be nice, but that would require making a new housing, and I can make do with that for the next few decades, I think. And another aspect that's also important to me is that I also want these arms to go down to very small diameters. So here I'm in positive lock with the set screw, and here too, and you see the design gives us a very small gap here so that the bearings can rotate freely, and we don't have to mind how far we adjust those. The lock is defined with the set screw. That's also a nice feature of that new design. Come on now, don't get tired. Right, so that's it. Nice. The older arms didn't allow for this because they just had a transition here. And now let's get rid of that second problem I mentioned in the beginning of the video. So here I'm just interpolation milling that radius that will allow that counterpiece to rotate freely out of the bed. Nice. So when you tighten the screw, this whatever you call this piece, it cannot slip out of there because it still is in positive lock with the bed. But in the loosening direction, you just have to turn it. That's nice, just like we want it. Nice. Alright guys, thanks a lot for staying with me until the end of this video. I appreciate your time. I hope you found the one or the other thing interesting, and I'll see you on the next one. Bye!